Thank you, everyone. Debugging performance is so much fun, right? Who here likes to debug performance problems? And well, quite a bit of you. Well, I love debugging some stuff, but performance problems is not really the thing I like most. So, of course, we don't like it, especially when the client comes screaming to your door, say, well, the site is slow, or whatever is slow. So, what's the current status quo for dealing with performance in our systems? Well, we do prevention. At least a few of us do prevention. Like we create, well, I come from a background of web development, so I'm going to talk a lot in terms of web development and audiences and things that you cannot control, how many people are going to be using your system at the same time and pounding on it. So I'm going to talk in terms of web services here. So what we usually do is we try to be critiquous in how we program the software so that it's not slow, so that it uses quick routines. But at the end of the day, you can only guarantee a certain service level. And you do that by doing functional performance testing of your system. You write a script that simulates how the user is going to interact with your site, and you run something that pounds your server with the simulation in parallel, many guys at the same time, so that you can say, well, we've proven that our system works for this amount of parallel users according to what our service level agreement says. Right? Everybody here does it? How many people do it? Okay, I got a couple of hands. And it should be done before production, right? So, and then after that, what happens? Well, you put the system online and you wait for the angry mob. And what we usually say when the angry mob comes, because it will come, is, well, can you have some reproduction instructions, like when exactly does your system get slow? Because I wasn't looking and I don't have anything in here to give it to me, but this is what most people actually end up doing. Although some people also do proactive monitoring. I was looking at the exposition stands, and there are quite a few people selling solutions for, well, we monitor your site, we have these metrics that work out of the box, and that's good. And some people do that, but usually these things don't tell you the whole story. They tell, oh, you have this part here that's slow, and we don't know exactly why. So we have to investigate, and if you, by some chance, some good luck, have some reproduction restrictions, like the client says, well, if you go here and click there and click the other thing, then it gets really slow. You can try using some Python profiling tools like Profile or cProfile, but you cannot use those in production because they make your site even slower, like hugely slow. So you have to have an isolated environment, and you can use these tools, but Profile specifically is something that every time I use it, I have to reread the manual all over again because it gives me this huge table full of numbers that I can never remember what they actually mean. How many of you have this same problem? Good. So, and the other thing with Profiler is that the numbers it gives you, it only shows the relationships between what functions called other functions and how long they took in the aggregate or individually. But you go look inside a function, it has a bunch of lines, you don't know exactly which lines caused the problem and in which situations. And you can clearly see that when you were developing your system, you called those same functions and you were not slow. So how do you do that? There's another tool that we learned recently called StatProf that is a little better in that regard because it does sampling of tracebacks and it collects the actual lines that, that were running at a certain time in snapshots. And if your system is slow, these snapshots will happen to collect, to hit exactly in what's going to be slow, so it gives you line numbers, so it's a little bit better, but it still doesn't tell you the whole story. And it's also lighter because cProfile is very heavy, so if you do sampling, you're just instrumenting a little bit of your system, it's not so heavy. But it doesn't tell you the whole story, like what exactly was this being called, why exactly is this taking so long in this situation. So when you don't have a production instructions, which is most of the time, what people tend to do is they put start and stop timing calls all over the code and put that into the log. We've all done that, we've all been there. The problem is, if you're doing this in production, that means you have to restart your system after you put your calls, and then you have your system admin banging you, just saying, why are you restarting the system? You cannot do that. That's not proper system maintenance. In Zope world, we have developed a tool called DeadlockDebugger, which is really nice because it gives you a snapshot of what's happening on the system at that moment. Well, since I'm going to talk about Zope, let me talk a little bit about what Zope is. Because the techniques I present here, they are generically useful for a number of servers, but man, I blanked. Oh, okay. They're generically useful for any situation where you have a worker model, where you have a listening process or a listening thread listening to your socket, and then it collects the request that came in and dispatches it to a thread or to a process that is going to handle that. So the Zope web app server, it has one listening thread listening to the socket and a fixed number of worker threads to which it delegates the actual work of rendering the request and returning it to the browser. It also means that if all your worker threads are busy, the rest of the requests will be slow. Zope is also transactional in the sense that when a request comes in, it starts a transaction and does the work. If anything goes wrong, it rolls back everything until the beginning of the transaction. If not, it commits everything at the end of the transaction, which means at the end at the point where the system returns the answer to the browser. This is only useful because I'm going to talk about the case later. But for everything else, keep in mind this model. You have one process listening to the requests and collecting all the network I/O and collecting the requests and dispatching to worker threads, and worker threads do their work and return the answer to the listening thread, which spits it out to the browser. So keep this model in mind. And what DeadlockDebugger does in Zope world is it has a special URL that it captures inside the listening thread. It does not dispatch it to the worker thread, and it executes this code there where it calls cscurrent frames, which is a call that every Python version after 2.5 has, and calculates a stack frame and renders it to you instantly. The great advantage to this is that even if all your worker threads are busy doing something and you don't know what they are doing, you can still go to this magical URL that is executed from the listening thread and get the full stack trace of what all the threads are executing. This is immensely useful. But it's only useful if the system is stuck right now when you're looking. So the client calls you, oh, it's slow, and then you go there and look at the URL and see, oh, it's doing this thing. So that's why it's slow, and you can reload it a couple of times and see, oh yeah, so this is what the system is doing. So what is this cscurrent frames call? It returns a Python dictionary where the keys are the IDs of the threads, and the values are the frame objects on the top of the tracebacks for each thread. What is this stack frame object? It contains information about the currently executing function, its file name, its line number, and a pointer to the previous frame. So we can reconstruct the whole call stack for the thread. So in the DeadlockDebugger, it provides you an instant snapshot of what the system is doing at the current point in time. So, and going back to proactive monitoring, what most people do is they parse the server logs to see what URLs that are slow, but in a model of worker threads, URL can be slow just because other URLs that came before it are slow, and so you don't have all the information. You can also have some other systems that report on specific parts of your stack, saying, well, this query in the database was low, but you sometimes don't know, so who called this SQL query that was so slow? Why is it being called this way? So can we do better than this? What if you could take this technique from DeadlockDebugger and run it continuously? What if we could run it and collect information only for the requests that were actually slow, and add some extra info to them to help you determine what exactly was happening? This is what a long request logger does, which is a product for Zope, but the technique is generic for any worker process or worker thread framework. It was designed by a couple of friends of mine, Julian Munchenblad and Sebastian Roman, along with me, and I implemented it. And what it does is intercepts every request, launches a thread, or reuses a thread to monitor it. And for every couple seconds after a certain timeout, it will take snapshots of the tracebacks and save them to a file, along with some additional information. So even then you have a log file saying this request of this URL is running for this number of seconds. It has this request information like the URL, query string, things like that. And then you have this stack trace. So it shows you which requests were slow, because you can see the count. Oh, this is taking 10 seconds, 12 seconds, 14 seconds. But it doesn't pollute your log with the requests that were slow just because other requests are slow and took all the available worker threads. So you don't have a pollution of information. And they show you why exactly these threads are slow and the right spots to add optimization. And I'm going to talk about that in a little bit inside the case study of the first big thing that we solved with this problem. ERP5 is enterprise resource planning system, like big management system written in Zope. It was running in this t-shirt custom printing company. It's actually some other thing completely unrelated to t-shirt printing, but I cannot talk about that, so let's pretend it's a t-shirt custom printing company. They had these horrible peaks of performance that were completely random. They were never twice on the same URL. And they were always at moment of high volume. So whenever we went on to investigate, we looked at those things and it was all right. There was nothing wrong with that. So how do we fix that? How do we find what went wrong? Well, I'm going to go like in those cooking shows where they say you mix all those ingredients and then you have this cake after 2 hours, and then they show you the cake ready. I'm going to show you the cake ready, which is the log files that we had. So you can see here the format of the log file. There's a lot of information, but to go step by step. So you have like a timestamp, which thread was running what, when it started, how long it's running for, oops, this one here, and what URL it is accessing, like this. And then it shows a bunch of information about the request, and after that, the traceback. So you have the file, the line number, the function that was being called, and you have a series of tracebacks every 2 seconds, for example, if you configure it for snapshotting at every 2 seconds. And if you put this traceback side by side, and but like this, what you have, don't try to read all this information, I'm going to show you something cool here, which is you have a cold part, which is a bunch of lines that don't change, then a hot part, which is a bunch of lines that are completely different between the 3 sequential requests, or 3 sequential snapshots of the same request. And the part that is low, the part that you actually have to optimize, is the limit between the two. Because the cold part is sitting there waiting for the hot part to finish running. So you know they shouldn't have to introduce any kind of caching or memoizing or recalculation. You do this at the exact point between the cold part of the stack frame and the hot part of the stack frame. In the case of ERP5, let's go back to playing it. In the case of ERP5, the culprit was a price line on the sale order of each t-shirt, because they had this custom t-shirt printing system that talked to ERP5, and they could order a large amount of t-shirts with different messages in it, but with the same characteristics that interfered with the price in each t-shirt. For example, you can have colors of the t-shirt, the number of colors of the printing of the messages on t-shirt, and things like that. Those things influence the price, but the actual message that's printed did not influence the price. So you can have like thousands of completely different t-shirts with more or less the same prices, or blocks of the same price. So what we did, and these prices, they were calculated the first time the order line was created and stored in the order line, so they didn't have to be calculated anymore. And the system was tuned to deal with large volumes of sale orders, but not with sale orders with large volumes of lines. Because when it had large volumes of lines, and the user tried to look at the sale order he just created, because it was created mechanically from an outside system, and when the user tried to look at it the first time, the prices were not calculated yet, so all the prices were calculated at the same time, because the sale order view had to show a total price. And so the user would spend hours looking at the spinning thing in the browser, waiting for the sale order calculation to be done, but it would only happen once. It would never be there to see it actually happening. But we had this system running, so we could go back to when the user said it was low. We could actually tabulate all the request information to see when it was low. And we could see, oh, it's happening when the prices are first calculated, because these routines only happen at the price calculation time, and the calculation only happens the first time that the user looks at the sale order. If he looked at it before background indexing of the sale order happened, which is why it was so random, which is why we could never look at it. And by looking at the cold and hot parts of the tracebacks, we saw, oh, we can optimize, the part we need to optimize is right here. And we can optimize it by caching the prices of these common characteristics of the t-shirts keyed on these characteristics, and put them in a transactional variable, and a variable that only exists during this transaction, so we don't have problems of having to erase this cache. The cache will disappear at the end of the transaction. But since this was happening in a single transaction, all the prices of the t-shirts being calculated at the same time, or actually one before the other, but in the same transaction, we didn't have to worry about anything. That's why the transactional part of Zope was important for us. So what we had was a death by 1,000 cuts, but long request logger helped us to focus on the exact part that we need to focus. There was also another case study in the Brazilian government. They had a website that from time to time was really slow. And they didn't know why it was low, and there was nothing in the requests that were or in the URLs that were good to show why they were slow. So with long request logger, they were able to see that the requests that were slow were requests that were doing lookups in the database that was in another machine, in a backend machine, and only in certain specific times. And they saw that these times coincided with the time where the backup was running, because the backup system used the same internal interface on the server machine as the database lookups. So they saw that it was a network problem, and they correlated the times, and they could figure it out why the system was low at that point. So as I said before, long request logger helps, or this technique helps you determine what to optimize by looking at the interface, or the middle point between where the stack frames are cold, meaning they are the same between all the snapshots, and where they are hot, meaning where they are different between all these lots. It could be the case where you have only cold snapshots. All the tracebacks are the same, including the last call. This means that the last call is doing something expensive, like querying a database. And it works, this technique works really well because since you're doing sampling, you're taking traceback snapshots from time to time, statistically you're bound to hit exactly when your system is low, because if you have subroutines in your requests that are calculated fast, the chance that they are taken by one of these snapshots is really small. So the snapshots are going to show you exactly what is going slow in your request. And you can, and since what you have with current frames is the stack frame object, you can do a lot more than just printing a stack trace. You can actually go and extract information like I showed you. We had information about the request. I will show a piece of code that does that. You can see here that we get the frame object. You can see the first red call here. In this function, we get the frame object and we loop through all the stack frames going back to each parent frame until we find one that has an object in its locals called request. And then we can fish the information out of this request to print it. So you can do that, you can do different kinds of things, like if I'm in a request that does database querying, I can take the SQL that was generated to do database querying and print that. So it's very flexible and can show you exactly what was happening and why it was happening. So this is some other technical stuff, because this talk was originally for a 45-minute talk. And what are the challenges of this technique? Well, there's the data volume. If you constantly have things going slow in your system and you leave this thing running, you get a really huge log really fast, so rotating it frequently is really important. And if you have many threads, long request logger will dump all the threads in the same log file, so you need to interleave based on the thread ID, which stack traces belong to one request or to the other. But that's easy to do, but it must be done. And the lack of user interface. Right now we only have this text file. You saw that I showed you the meld, which is exactly what I use to compare stack traces. It would be perhaps interesting to have something that would parse all these requests, tabulate which requests were longer, which URLs are more likely to cause request problems. It would be nice to have things like that, and then have a nice user interface showing that you can click between all these stack traces to compare them. And let's talk about future improvements. I'd like to make this into a usable library and write user interfaces and helpers for analytics, like I said before, and have a more pluggable way of pulling information from out of the frames. If we could put that in a structured log storage, we could do queries and richer comparisons, and it would also be nice if we could tell the system to ignore certain requests that we know we are going to be slow because they're only done by internal systems. There are also some open questions like, what is the true performance impact? This tool, I use it for sites that have sometimes they have requests that are slow, and in general it's very lightweight. It doesn't interfere. We don't feel any impact on it's simply leaving it running on the system, which is why it's good for production. But if you have a really speedy system that loops really fast and you're trying to locate something really small, you could have some great interpreter lock contention. The talk before this one was talking about the absence of a great interpreter lock in Python, which would be nice. But since this is using one thread to monitor another thread, you could have a problem where the thread that's doing the monitor is actually competing for CPU resources with the thread that's being monitored. So we could perhaps optimize by having a single thread monitoring all the others. There are some improvements we can do, but overall, I'm very happy with this technique, and it's been used to solve some really hard problems in some complicated cases. And it's good because you can just leave it running, and when the client complains, or if some other monitoring tool complains, you can go there and go back in time and see what exactly the system was doing in only exactly these low requests. So it was really nice. Here's some references for this talk, and that's it. I hope you guys liked it, and if you have questions, please feel free.
So as before, if anyone has any questions, please come up to the question mic.
So I'm Shane Hathaway.
Hi Shane, nice to meet you.
Hello.
Nice finding you again, a long time ago.
Yeah, so I've used Long Request Logger, and I actually turned it into a reusable library for WSGI and Pyramid apps. And it's called SlowLog. I just thought I'd put that out there.
Thanks.
Hi, really short question. Does this syscurrent traces call work if you're using Gevent in your service? If you're using what? Gevent, which is a greenlet thread thingy.
So everybody answered him already? I haven't tried. My intuition says that, well, it will give you something, but it might not be exactly what you expect. It will certainly give you one traceback per thread, but it will not give you one traceback for greenlet, per greenlet.
Fair enough. I guess I will just try it out and see what happens. Thank you.
Okay.
Hi, so my first question is actually going to be about tools used for like diffing and comparison and stuff, but I guess you kind of answered that. The other question was like, do you actually print out information that's not just on the stack, like maybe class variables or other sort of like other information that might impact something? Because I'm thinking in terms of like, you know, if you're running like a same function over and over again, and like maybe you're like doing like cache miss each time with a certain like order of input versus you know, another order of input like gives you like better caching results or something. So like, can you debug problems like that as well?
You can, since syscurrent frames gives you a stack frame, which gives you the chain of stack frames, you can actually do many things with it, like it gives you the dictionary of locals and of globals of the function, so you can actually evaluate any Python statement on that environment. But you need to be careful because if you're in a threaded environment and you have locks and things like that, if you call a function that for some reason triggers a lock, you could leave the system in a deadlocked state because you're messing with the internal expectations of the thread that's running that frame. But in general, you can actually run anything you want or evaluate any kind of Python code within the locals and globals of each frame in each stack. So it's actually quite powerful in that direction. Okay, thank you very much.